Now let's go ahead and solve our familiar left-hand side, but with the new Dirac delta function. So we have x double prime plus 4x prime minus 21x is equal to, and we'll do the Dirac delta at 3. We'll keep our x of 0 equals 1, x prime of 0 equals 0. So I take that Laplace transform, x double prime 4x prime minus 21x equals Laplace transform of the Dirac delta function at 3. And so what we know from doing this a bunch of times is that when we take that Laplace transform and we're getting some eggs at the door, so yeah, that's the background. So we have s squared plus 4s minus 21 x, and then we had the minus s and the minus 4, which we bring to the right hand side, so we have that. And then our Laplace transform of that Dirac delta function, we get e to the minus 3s. Okay, so we have that, and so we'll divide both sides by our polynomial there. So we have our s plus 4 over s squared plus 4s minus 21 plus our e to the minus 3s over s squared plus 4s minus 21. Now we need to do our partial fractions for the s plus 4. We've done that, so I'm not going to show that again. I'll just end up putting the answer. But let's go over here and do 1 over s squared, this part without the e to the minus 3s. So I'll go to a new page, and so I want to do my partial fractions decomposition of this one, and so we need an s over s minus 3, and an a over s minus 3, and a b over s plus 7. Again, multiply both sides, or get the common denominator, I guess is really what we go with, and look at the numerator, and we'll have s plus 7 like that, and then b times s minus 3. I'm going to let s equal 3. When I do that, I'll get 1 equals 10 times a, so a is 1/10. If I let s equal -7, that's going to imply putting -7 in there, so I'll get a -10, so b is minus 1/10. Okay, so I do that, I go back, and so this is equal to, now my decomposition before for this first part, I had 7 over 10 times s minus 3, and then plus 3 over 10 times s plus 7. And then I have my e to the minus 3s, and that's times the 1 over, let's see, that was s minus 1 over 10 s minus 3, and then plus 1 over 10, minus 1 over 10 s plus 7. Okay, now we need the inverse Laplace transform, and so again this was uppercase X, we need to make sure it looks that way. And so now when we do the inverse Laplace transform, we have our lowercase x of t, and we have from this first part 7 over 10, And we've done this a bunch of times. We know this is e to the 3t plus 3 over 10 e to the minus 7t. Now, then we get this part over here, and remember that we just do the inverse Laplace transforms of each of these pieces, and well, I know what those are. I get 1/10 e to the 3t, and over here I get minus 1/10 e to the negative 7t. But this part introduced that unit step function or Heaviside function. Now I've got a 10th in both of those, so I'm going to factor that out as well. So I could write this as u or an h, uppercase H for Heaviside, u3 of t, or, well, I could do the u of t minus 3. That possibly helps remind us of this substitution then. So we have our e to the 3 t minus 3, because that's what we have to do for that inverse Laplace transform, and e to the minus 7 minus there, t minus 3. And so that's what we get for our solution. We have that Heaviside function, and so again, another way to read this is simply that this is a piecewise function. So we have x of t is equal to 7 over 10 e to the 3t plus 3 over 10 e to the negative 7t for 0 less than or equal to t less than 3. And then when we hit the 3, we have that same first part, so 7 over 10 e to the 3t plus 3 over 10 e to the minus 7t plus, and I'll just make it 1/10, because the unit step function up here, that part just becomes 1 at that point, and so then times e to the 3 t minus 3 minus e to the 7 t minus 3. And there we have it. So you can write it with the unit step function in there like we did up here, or you can write it as a piecewise function. But the point is, that's all that unit step function is doing. It's a way to do this piecewise function, but not have it look like a piecewise function. You know, is that aesthetically pleasing? I don't know. You know, either way, as long as you have the vocabulary, they are both saying the same thing, and so in one sense it doesn't matter. But again, from the idea of this Laplace transform, it becomes kind of transparent to do that, whereas when we didn't use the Laplace transform, we had to attack things sort of more this way. And of course, in this case, with that impulse function up here that we have, the problem is I don't know how to do that other than with a Laplace transform. Now, I say I don't know how to do that. I mean, we will look probably at some numerical ways to get at this. Pretty much what you use is the d tau function, and you just make tau really, really tiny. But using the Laplace transform in this case is just a much nicer way to attack it. You know, it just falls out better. All right, so there's a solution with an impulse function, and we'll stop there.